The background behind trying to pronounce my full name is the following. At some point, when I stopped being a young member of the university community, I realized that the whole university, or maybe not the whole university, the whole faculty, starting from the cleaning lady and ending at the dean, calls me Miss Kasia. And there are, of course, professors that are called Professor XYZ. And there are doctors that are called Doctors XYZ. And I'm Miss Kasia. So I'm Miss Kasia. Okay. So we have finished last time with essentially, it doesn't work. I should switch it on. Here, it works. We have finished with discussing double vector bundles and the concept of linearity. And we came back to Tulczyjew triple, which we expressed as a diagram composed of morphism of double vector bundles. And we were about to embark on examples. And I have prepared two examples, which is one is relativistic particle with mass, and another is a relativistic particle without mass, which are called classical photon, because we are still in the realm of classical mechanics. Therefore, for example, there is no way of distinguish between, I don't know, neutrinos, photons, and whatever. All this stuff is one kind of particle without mass. So this was our classical Tulczyjew triple, composed of three double vector bundles. Here is the diagram with all the details, all the double vector bundle structure of all the ingredients. And the main idea is that our differential equation, which is phase equation, I mean equation on curves in the phase space. This equation is some subset, usually a submanifold, usually a Lagrangian submanifold of the tangent vectors to the phase space. And this equation can be obtained in two ways. One is Lagrangian mechanics, when we are given a function on vectors, and out of the function we produce, using the structure, we produce this equation. And if there are no constraints, then the procedure is the following. We take the differential and the image of the differential of the Lagrangian, and then we use the inverse of this map. This map is an isomorphism, therefore no problem with taking the inverse, and we obtain a subset here. If we are given a Hamiltonian, and again, if there are no constraints, we just take the image of the differential of the Hamiltonian, use an appropriate isomorphism. This time, this isomorphism comes from the symplectic structure, and we obtain a subset here. Starting from Hamiltonian, we always have an explicit dynamics, in the sense that this subset is an image of some vector field, the Hamiltonian vector field. If we start from Hamiltonian, sometimes we can obtain implicit dynamics. It is explicit for regular Lagrangians, and we can see it here on this picture. If how do we produce Legendre map? I mean, the correspondence between velocities and momenta. We take the differential of the Lagrangian and we project with the other projection from the double vector bundle here. And if this map is one-to-one, then this section, the image of this section is also an image of some section here. We have an isomorphism of double vector bundles. It means that the whole stuff translates into the middle, and again we have a section here, which means a vector field. But if this map is not one-to-one, then we don't have a field. But we still have a valid equation, and now those examples.
what physicists sometimes say, that Lagrangian is equivalent with Hamiltonian picture.
No, but you know, what does it mean equivalent? It is subject of discussion, but maybe it is not. Maybe we shouldn't say it is not true. It depends on the interpretation. Okay, so my first example will be an example of free relativistic particle of mass m. And to make things very simple, I will work in the affine Minkowski space. This way, I just forget all the differential intricacies in a sense. I can separate my velocities from my positions and my momenta from my positions. My phase space is then just the affine space with the Cartesian, the positions and momenta are elements of the dual space of the model vector space for this affine space. And for the Minkowski matrix, I use the sign convention with plus and 3 minuses, which is the opposite of what usually physicists do, but it will be, I mean, it doesn't matter. It is just more, it's easier for me. And since it's an affine space, all those iterated bundles can be also written in trivial form as Cartesian product of the affine space as position and the appropriate order of dual vector spaces and the original model vector space. Both maps, beta and alpha, are there just reorderings of components here with occasional minus somewhere, for example, here. Okay, now what Lagrangian I have? My Lagrangian is defined on positions and velocities. So it does not depend on positions, but formally they are there. It depends on velocities which are positive with respect to this eta. So there are time-like vectors inside the cone. If we decide to choose one half of the cone as future and one half of the cone as past, we additionally have an orientation. But we just take this open subset of time-like vectors. It is a kind of constraint, but from the point of view of differential geometry, it is not really a constraint, not a problem, because it is an open subset. So everything works as on the whole manifold. Here is the Lagrangian. This is up to constants that we can choose to be 1 or forget. There is just the length of the Minkowski length of this vector. Why it is a good choice? Because this Lagrangian is positively homogeneous, which means that our action does not depend on the parametrization of the world line, which is good, because in relativity, what we are dealing with are the space-time trajectories, world lines, which need not to be parameterized. Of course, if it is a time-like trajectory, we can parameterize it by the proper time, and it is okay. But then if we want velocities that gives us this proper time parameterization, then we have this problem with constraints, because we only have length 1 vectors, and we have to deal with it. But with this positively homogeneous function, our action does not depend on parameterization, so things that are not physical do not interfere in our model. Okay, so then...
Paths, but submanifolds.
Yes, there are submanifolds, yes. But not only. We will see what is because the approach is that we are looking for equation on curves still, because we are applying this machinery. So we will see what will be the result, what will be the solution of the equation that we will in a moment obtain. So we apply the machinery, we take differential of the Lagrangian. Since the Lagrangian does not depend on positions, then we have here positions, here velocities, and 0. This is change of the not the change. This is the differential in the direction of positions. It is 0 because the Lagrangian does not depend on that. Eta is the constant metric here. And we differentiate with respect to the velocities, which means that we obtain here the momenta. And then we can look at the Legendre map that associates to every velocity its momentum. And the result is that this is definitely not invertible, because when you can see that if I multiply my velocity by a positive number, the momentum does not change. It's the same momentum. Okay, so then I use alpha to get my dynamics. And this alpha is just changing the order of things. So I have a position, I have a momentum, but not every momentum can be obtained. Not every element of V star can be obtained. Only those momenta that live on the so-called mass shell. So the square of the momentum has to be m squared, c squared. If you use c equal to 1, it means that this is just m squared. So there are Hamiltonian constraints. They appear constraints on momenta. And then the velocity can be whatever obtained from, there should be probably be this tilde here, or tilde to the -1 as a matter of fact. Because this is the velocity that corresponds to momentum via this map, but it can be multiplied by any positive number. This positive number is the length of the velocity. Since the length of the velocity doesn't matter. Whatever velocity I take along the same line, I get the same momentum. So the velocity, but this number should be positive because it comes from the length of the velocity. And here I have the change of p. So since p dot equals to 0, it means that p doesn't change. I have a conservation law. Once I have a momentum, it stays the same. So this is my dynamics. What are the solutions of this dynamics? No, the solutions are, of course, straight lines in the Minkowski space, lines that lie inside the light cone. So there are time-like straight lines. Here I have those, the mass shell. Some of the momenta are on one part of this mass shell. This is the two-sheet hyperboloid. So some of the momenta are here, some of the momenta are here. And for the blue momentum, I get the straight line, which is oriented to the future, assuming that I've decided that up there I have future and down there I have past. So for this momentum, I get as a solution a straight line with proper direction given by this momentum. And since I only accept velocities that are multiplied by a positive number, the result is that it is not parametrized, but this is oriented. So I have an oriented line as a solution. All the parameterizations are okay as long as they go towards the future. And for the momenta that are on the other part of the one-sheet hyperboloid, I got straight lines, time-like straight lines that are oriented toward the past. So this way we have discovered Feynman antiparticles on the classical level, which is a little bit funny probably, but it is like that. When we look at this dynamics, it is definitely not the image of a vector space, a vector field. On one hand, it is not over the whole phase space. There are constraints on the Hamiltonian level. On the phase space, there are constraints. And once we fix position and momentum, we have the whole half distribution of the vectors on the mass shell. Geometrically speaking, we have this mass shell, which is two-sheet hyperboloid. Since in the cotangent space, in the cotangent bundle, it is a level set of one function, it means it is a coisotropic submanifold. It has its characteristic distribution, and the dynamics is just half of this distribution because we have this orientation. So one half up there and the other half down there. So now we can ask the question, okay, can we obtain it somehow from the Hamiltonian side of the triple? And the answer is we can, however, definitely not from one Hamiltonian, because it is not a vector field. One way to obtain a similar differential equation is just to take a function equal to 0 on the mass shell. Then what it generates, if I have a function on a submanifold, I can generate a Lagrangian submanifold taking all the covectors attached only on the submanifold, such that when they are applied to tangent vector to this submanifold, they give the same as a differential of the function. It means that I have something like differential of the function on the submanifold plus the whole annihilator of the tangent bundle to this submanifold. So the dimension on the position is restricted to the submanifold, but the dimension along the fibers is enlarged. So still it is a Lagrangian submanifold in some sense. So I can do that for this, but then what I lose is this orientation, because what I get from the function equal 0 on the coisotropic submanifold is its characteristic distribution. So the whole distribution is generated, not the half of it. If I want a half of the distribution, I need more sophisticated generating object, which is called family of functions. The proper object is written here. It is a function of position, momenta, and additional parameter. This additional parameter here should be a positive real number. So this is a function of the three things. You see that on the mass shell it is 0, but technically it is something different. So how do we generate a Lagrangian submanifold from the object like that? In general, we can try to generate Lagrangian submanifold on T star n, starting from function which is defined over the total space of some bundle over n. And the procedure is the following. We take the differential of this function and we intersect it with the annihilator of vertical vectors. It means that we look for such points in F that this function has vertical differential 0. The differential vanishes of vectors vertical with respect to this projection. And then at these points, the differential is really a pullback of some covector from n to this particular point. There are, of course, some conditions for H to ensure that what we get from here is really a submanifold, because this procedure gives us some set that can be strange. But we can list the conditions, and then we know that what we got is a submanifold, provided that we need a submanifold, not a subset. Sometimes we can be happy with the subset. But in general, if we want a Lagrangian submanifold, there are some conditions. This way, we can, for example, generate a a Lagrangian submanifold which looks like two copies of sections. Yeah, imagine the image of the closed one form is always a Lagrangian submanifold. Yeah. So if we have one image of one form and the other image of the other form, and we want to generate this simultaneously, this is the way we can do it. Or things that go like that. This is the way we can do it. This is the most general generating object for Lagrangian submanifolds that we can invent. The details with all the proofs and all the recipes can be found in the book Symplectic Geometry and Mechanics by Marle and Lieberman. A very, very good book, very detailed, and everything is there with the proofs. As for our case, so for the problem of finding Hamiltonian generating family, the structure gives us a universal generating family. You definitely recognize this formula. This is when somebody asks you to write down a Legendre transformation, you either write this thing, which means momentum coming from the Lagrangian, or you write this formula, Hamiltonian associated to the Lagrangian. And what do? We to find Legendre map, so to translate Lagrangian to Hamiltonian, we differentiate with respect to velocity and look for stationary points. This is exactly doing this vertical differential and looking for points where the differential of the generating family of functions, vertical differential vanishes. So this is what we do. So our universal degenerating family is parametrized by velocities, and if Lagrangian is regular, then this family can be simplified. It means that we can find a section of this F such that on this section the vertical differential vanishes, and then we evaluate this function, which is initially of P and V. We evaluate it on this section, and we get just one function, one Hamiltonian. If it is not the case, and the Lagrangian is not invertible, not regular, Legendre map is not invertible, then we can sometimes simplify a little bit this generating function. For example, find some family of points when the condition is satisfied, and reduce the number of these parameters. But sometimes some parameters are left. In our case of this dynamics, we definitely need one out of all the velocities. It should be M here, and it should be, not Q. It is just the artifact. I sometimes use Q for positions and sometimes use M for positions, and then things get mixed. So M here. We can just forget about almost all the information about the velocity, but the length, and then it is this parameter for the family that we can know. We can also take an excursion in the direction of symplectic relations, and then we can observe that this function of positions and momenta attached at the same point is a generating object of our symplectomorphism between the left and right hand side of the Tulczyjew triple. If we treat them as symplectic relations, this is the generating object. So we have one symplectic relation generated by Lagrangian. It is the image of the differential of the Lagrangian. The other symplectic relation, it is this, and then we compose it, and on the level of generating objects, composing symplectic relation means adding generating objects. It is, of course, many details are here. I'm just I'm just pointing you in the right direction if you really want to know more about this. Okay, so that's that. The first example. Now we pass to the second example, which is massless relativistic particle. Again, we are on the Minkowski space. Again, it is an affine space. And now I start with the dynamics. What do we need for the massless particle? The massless particle should travel with the speed of light. So the velocity should lie on the cone. And also on the dual side, the momentum should also lie on the cone. And we know that the momentum of the photon is somehow related to the frequency. So if the photon just travels through space and nothing happens, it's not interacting, this momentum shouldn't change. So the frequency shouldn't change. Therefore, we definitely need fixed momentum and p dot equal to 0. And we need the velocity which lies on the cone, and essentially gain is whatever. And then on the classical level, do we need to distinguish from photons and antiphotons? I'm not sure. Photons and antiphotons are the same. However, neutrinos and antineutrinos are not. So maybe if we think about the classical massless particles, we should also distinguish between future and past. Therefore, I again require this real number here to be a positive real number. And this is the dynamics. And this is again a Lagrangian submanifold of T star M. Is it generated somehow from something? In this case, it is not generated from Lagrangian, one function, and it is also not generated from the Hamiltonian, one function. Both are generated by the families of functions. Here are the pictures, particles on the cone. So I have again momentum in the past, momentum in future, and those straight lines lying on the cones. And here I have an examples, of course, generating functions are not unique. If you have generating families are not unique. If you have a Lagrangian submanifold which is generated by a function, then the only freedom you have is this function can be changed by the constant number, because this is the differential. Yes. So in the case of generating families, there is much more freedom. These are examples of such families, and those two families are again related by Legendre transformation, in the sense that you add this generating object of the relation between Lagrangian side and Hamiltonian side, and you try to simplify it somehow. As you can see, again, there is, if we think of in terms of function defined on the cone, so on the mass, this time mass shell is the cone without the origin, then we can think in terms of function 0 on the cone. What we lose is again the orientation. We have really photons, so we don't distinguish between photons and antiphotons. And then 0 function on the cone on the Lagrangian side, and 0 function on the cone on the Hamiltonian side generates us exactly what we need. This is our differential equation. Okay, so we have now two examples of the application of this generalized structure to some kind of physical systems, and we can pass to There is still one slide. Sorry, I forgot. If you need more examples like that, you can consult a paper with the title Slow and Careful Legendre Transformation for Singular Lagrangian. The origin of this strange title, Slow and Careful, comes from some discussions between Tulczyjew and Marsden. I think that they were in the constant, maybe not even discussion, it was a war and insulting each other in public. So Tulczyjew was once advised that while doing Legendre transformation, he should be slow and careful. So he decided, okay, I will be slow and careful, and this is the result of the paper.
In contrast to Marsden, who wrote a paper starting with a quick introduction or something. Yeah. So this is not should be quick, but should be slow.
But he also said that you should be. Oh, but okay, maybe I'm wrong. Definitely, it is the problem about discussion between Marsden and Tulczyjew. There are several examples here, and the co-author is Paweł Urbański, who is present also on the slide. Okay, so now we have finished this part, and we can generalize ourselves for the first time, and this will be the generalization of the Tulczyjew triple for algebroids. Lie algebroids first, and then more general examples of algebroids. What we start with is an overview of the structure of Hamiltonian mechanics, very short. So what we did, we stated that, and also other speakers yesterday and today stated that Hamiltonian mechanics tend to be associated with phase space, which is symplectic or Poisson manifold. Then the structure is used to produce a vector field from a function. This structure is used as a map. So we extract a map from omega or from lambda, and we use it as a map. And then we obtain something which Hamiltonian equations in Darboux coordinates in symplectic case looks as follows. And using the Poisson bracket, we can also say how some function evolves along the solutions, calculating the Poisson bracket with Hamiltonian. Lux curve, yes, this is the Lux curve. And then there is a question, okay, so what is the structure responsible for Lagrangian mechanics? Here we have this Poisson or symplectic, and what we have here. And the answer is, it is an algebroid. Lagrangian mechanics, in a sense, lives on the tangent bundle, in most cases. The Lagrangian function can give us Euler-Lagrange equations and definition of momenta if we use the tools of variational calculus, or when we use the Tulczyjew approach, we can directly get the phase equation from Lagrangian. What is the geometric structure that is responsible for this map? So the answer is, it is an algebroid. It is an algebroid, therefore we will now shortly review different possible definition of the algebroid. And then you will see at the end that really the Tulczyjew triple on algebroid is two of the definitions, of the several definitions I will present written on one diagram. Okay, so what is an algebroid? The standard definition of Lie algebroid is the following. You have a vector bundle. You have a bracket on the sections on that vector bundle together with some vector bundle morphism. And there are conditions. The bracket should be antisymmetric. The bracket should fulfill Jacobi identity. And here I wrote Jacobi identity in a little different manner that it was written by previous speakers because I wrote it as to emphasize the fact that taking a bracket is a derivation of the bracket itself. Then, in case we need to write a Jacobi identity for the bracket which is not antisymmetric, we can use this formula, and it will work. And there is also the condition, or it comes out from it is the result of the previous conditions, that if you multiply a section by a function and take the bracket, the anchor appears here. This anchor is a morphism of the brackets, in the sense that I have a bracket of vector fields here and a bracket of sections here, and this should be a morphism of the brackets. What are the examples? The first example is maybe we can say the trivial one, but important, the canonical definitely. The tangent bundle itself, equipped with Lie bracket of vector fields and with the identity of as an anchor, it is a Lie algebroid. Another examples on the other extreme is we can take a Lie algebra, finite dimensional Lie algebra. We are in the finite dimensional setting here, treated as a bundle over one point manifold, and take the bracket and take the zero map as anchor, assuming that the tangent bundle of the one point manifold contains only one vector, which is a zero vector. So this is another example. There are, of course, more intermediate examples, something in between the bundle over one point and the full tangent bundle. For example, we can take a principal bundle with some group acting, and we can define something which is called a Tulczyjew algebroid. As a manifold, it comes out from quotiening the tangent bundle by the group action, and sections of the Tulczyjew algebroid come from invariant vector fields on the total space of the principal bundle. Anchor is just the tangent of the projection here. So this is another example. There are more, but we don't need them at this moment. So this was the first definition, shortened here, first definition of an algebroid. Another definition of a Lie algebroid. If we have something on E, we immediately have something on E star, on the dual side. And what we do have associated to an algebroid is a Poisson structure on E star, which is linear. Linear means that it is closed on linear functions. The relation with respect to the relation with the bracket is written here. So if you take a linear function that corresponds to the section of E bundle and take the bracket of them, you get a linear function that corresponds to the bracket of sections. And also you know how to deal with functions that are pullbacked from the base. So here is this correspondence between sections of bundle E and linear functions on bundle E star. Linearity also can be expressed as just compatibility with a vector bundle structure of E star over M. And since we decided to talk about vector bundles as equipped with homogeneity structure coming from multiplication of vectors by real, we can also express linearity in this way. It means the Poisson structure is linear if it is homogeneous of degree -1. Homogeneous of degree -1 means that if I take, for example, can mean that if I take the Lie derivative along the Euler vector field, I get minus the initial by vector. So this is the second definition. So you can have bracket, you can have a linear Poisson structure on the dual, and there are more. On the level of Tm, we have a Lie bracket of functions here and the symplectic structure on T star m. So this is the first definition, the second symplectic structure on T star m. Then another approach could be via the derivation defined on of sections of exterior power of E star. And again, this derivation here can be defined in similar manner as Cartan so-called magic formula for differentiating forms. For one form, so just the section of E star, I will get something like that. So a section, if I want to evaluate this differential on two sections, I write a formula like a Cartan formula. The difference is that whenever I need to act on a function, I have to apply the anchor, and the bracket of vector fields is replaced by the bracket of section. So this is the relation between this differential and the bracket. And again, if we are on the level of this canonical example Tm, this d is just the Deriving derivative. And this is exactly, again, the same as symplectic, as Lie bracket. The Lie derivative contains the same information. So the fourth way to define the Lie algebroid is to look at the proper morphism. And now we are coming to the alpha. Lie algebroid can be defined as a certain double vector bundle morphism between T star E and T E star. The conditions are that it has to be over the identity of E star. Then the map down there on one of the legs of the double vector bundle is rho. And of course, it is not that easy to express other conditions. So antisymmetricity of the bracket and Jacobi identity. The easiest way is to do it just in the following way. Since we know that T star E and T star E star are always isomorphic, we can compose this epsilon with the isomorphism, then obtain a bivector, then obtain a map coming from some tensor. The linearity gives us that this comes from some tensor, linear one. And then we can say, okay, this represents an algebroid when this represents a Poisson tensor. So this may be cheating a little bit, but it is effective. If we want to use coordinates, of course, we can do it. And then as a map, it will contain some information about the anchor here, and it will contain so-called structure functions for the bracket, and the fact that it is antisymmetric is reflected in the fact that here and here we have essentially the same matrix. If it is any vector bundle, double vector bundle morphism over the identity, we could have here different matrices, but we have the same, and this is from antisymmetricity. And also those functions should be antisymmetric with respect to the lower indices, and the Jacobi identity could be expressed as some condition, the proper condition on the functions. So this is the fourth and the last that we'll definitely will not use is we can think in super geometric language, very short definition. If we think about our bundle as a super manifold, if we superize it, changing the grading on the fiber coordinates, making it odd coordinates, then our super function corresponds to sections of the Grassmann algebra, and then our dE is just a vector field, the homological vector field on the super manifold associated to this bundle. But this is just for completeness of the exposition, yes.
Is that related to 3 or is that different?
Is that related to what?
Is that related to number 3 somehow?
Yes, of course, yes. This is just the super geometric expression of this differential.
Okay, but
This is the same derivative, but look from different perspectives.
Okay, fair enough, yeah. Okay.
But this is all the same structure looked at from different points of view. Five possible.
The RAM acts on differential forms, the Grassmann algebra, but differential forms are functions on the superized tangent bundle.
Yeah, and finally we arrived to the Tulczyjew triple for an algebroid. We've been talking about Lie algebroid up to now, so let us stick to Lie algebroid. So we took definition 2, which is Poisson structure on the dual, but this Poisson structure written as a map. Since it is linear Poisson structure, it corresponds to a double vector bundle morphism here. And we took the definition 4, which provides us the epsilon map. We put it on one diagram. It is over the identity on E star, and down there we have the anchor map for the Lagrangian. So as a matter of fact, the Tulczyjew triple is just algebroid written, the two definitions put together in one diagram. But it works from the point of view of generating an equation on the phase space. The phase space is now E star. It looks as it did before. We could have Lagrangian, which is now defined on E. We take the differential and we transform the image of the differential from T star E to T E star. We obtain a submanifold here, which is it is now not Lagrangian. This is not Lagrangian. These are symplectic, but these are not isomorphism usually. So this is not symplectic space, and it is there is no notion of Lagrangian submanifold here. But still, we have a subset which is our differential equation. Or we can do the same from the Hamiltonian side. We have a function on E star, we differentiate, and so on. Again, what happens here and what happens here can be related by this time a symplectic relation between Hamiltonian side and Lagrangian side, which always exists. So these two things, the Lagrangian side and Hamiltonian side, they are isomorphic, and those maps are the structure of Lie algebroid expressed in this way. Can we extract somehow something like Euler-Lagrange equations from here? The answer is yes, we do. However, here we have this phenomenon that in one example, in one construction, one may have several ways of doing the same. So Euler-Lagrange equation can be extracted from variational calculus. You can write down it in coordinates and generalize. And there are like at least 5 ways to do it geometrically. Usually what people do, if you want to start from the dynamics, there is a very easy way. You just prolong the dynamics, take the tangent of D, then you intersect it with holonomic vectors, which means vectors that project on the same from the right and left and they correspond to second-order derivatives, but this lives on the phase space, and you project it down to T star M. And this is exactly, if you start from dynamics generated by Lagrangian, this is exactly Euler-Lagrange equation as a subset in second-order jets, written here. Of course,
Also implicit, yes, also implicit.
But this is something you cannot repeat in the algebroid sense, in the algebroid setting, because your curves, your solutions are either curves in E star, then these are phase curves, or if you want curves on something that corresponds to the curves in the positions, they should be curves really in E, satisfying some compatibility conditions, some admissibility, maybe not compatibility, but admissibility conditions that is related to the anchor, and that says that time prolongation of the projection of the curve should be with some agreement with the curve up there. However, one of the possibilities of extracting Euler-Lagrange equation does translate to the algebroid level. So if you write Euler-Lagrange equation in this form, that this is first order equation on the first order elements, so first order equation on velocities, not momenta, velocities, then you can look in the following way. You can take the differential of the Lagrangian and compose with epsilon or alpha if you are in this case, or you can go first via Legendre map, then here we have an identity, and then here we take the prolongation, so the tangent vector to the curve. So I can say, okay, my curve is a solution of Euler-Lagrange equation if I go this way, and I get the same. And we can check by calculation that this is exactly what we need. For example, if we take E equal to Tm, we get the usual form of the Euler-Lagrange equation. So we can think a little bit like that. Yeah.
Yes. Yes. So, okay. So maybe just we finish with this Euler-Lagrange question. So if I do that, I will obtain something which in coordinates looks here. So I get this admissibility condition, and I get almost as Euler-Lagrange equation in the usual case. So there is a prolongation with respect to time of my momenta here, and there is this part, and there appear structure constants. If we want to be sure that this is what we really need, we can do the exercise. So take E equal to Tm. Instead of usual coordinates with dot, introduce different bases on the tangent bundle, and just change the coordinates using these different bases, and try to express usual Euler-Lagrange equation in these different bases. You will get things like that. The details can be found in this paper, Geometrical Mechanics on Algebroids. And of course, there is a question, do we need this? And this is the moment when I should present the examples. And again, examples will be tomorrow, as before. And now I'm done for today. If you have some questions, it's the moment for the questions.
Okay, thank you. Any questions?
How do I think about this submanifold U? What is
this is okay. So this is a moment when these examples should be useful. So think of rigid body. Rigid body can be described on SO3 group with invariant Lagrange. If it is free rigid body, it can be invariant, a Lagrangian which is invariant. Then you can think of it not as living on the group, in the tangent space to the group, but living on the algebra only, because you can forget of positions. Then the phase space will be the dual of the algebra, and you can look for curves on the dual of the algebra. And my D is exactly the equation for those curves. First order equation on the dual of the Lie algebra. And I will get precisely, this is called Euler-Poincaré, I suppose, or something like that equation, and on the dual of the Lie algebra, and I will get it tomorrow from this construction. This is one example. Another example will be related to some constraint mechanical system, and this will be, we can think in general of so-called mechanical systems, so systems with Lagrangian of the form kinetic energy and potential energy, and no fancy stuff, but just like that, or just very simple example of a skater on the ice rink can be described on this way. And then this phase space is not that explicit. I mean, there are only those momenta that are important. If the skate can go only in the direction of its position. It can rotate, but it cannot move perpendicular to its position. Yeah. So we don't have free we have free position, free possibilities, free degrees of freedom for the position. Moving on the plane and rotating, so position on the plane 2 degrees of freedom, and rotating the third one. But the momenta are only 2 because we have the velocities are restricted, so momenta are also restricted. So what we get is a curve in this artificial, in the sense, restricted momentum.
So is it related to sub-Riemannian geometry?
Sub-Riemannian, I don't know. Probably is, yes.
So I have a remark. So these equations on the algebroids is a sort of universal reduction. So when you have a Lagrangian which is invariant, so if your configuration space is a Lie group, for instance, or a principal bundle, and you consider standard mechanics on it, on the tangent bundle of this, and the Lagrangian is invariant, then there is procedure of reduction of this to a smaller dimensional manifold, which is actually a Lie algebroid. In the first case is the Lie algebra, or the dual Lie algebra of this group, and you obtain Euler equations, roughly speaking. Yeah? In the case of principal bundle, you get something which is called Poincaré, maybe Euler-Poincaré equations. But also, because Lie algebroids, together with Lie groupoids for some kind of Lie theory. So this can you do also for mechanics on groupoids. Yeah, if you have some symmetries, you can reduce. If you want to do it in every specific case, so you should do all these calculations in every case. Now you can just, if you know that this is invariant, you can just directly go to the Lie algebroid and write down the equations which are given here. Yeah, so this is, so Lie algebroid mechanics is a reduction of Lie groupoid mechanics.
There is no remark or question. We can thank again the speaker.